This is part 2 of our discussion of section 3.3, projections. Okay, so the point here is that sometimes you want to be able to decompose a vector into two different pieces or two different parts. This comes up in physics somewhat frequently. So suppose that you have a car and it's sitting on a ramp or a hill. So I'm drawing the ground and here's like a ramp, okay, or a hill. And here's a car. I'm going to draw a very rudimentary looking car. Okay, there's a car. Now the weight of the car is a vector that points down because of gravity, okay? So this vector that I'm drawing right here, that's the weight going down. But of course, the car wants to roll down the hill. It wants to roll backwards, right? So some part of the weight is actually pointing down the hill. So let's get out another color. It's about like this. So this vector that I'm drawing in red right here, that is a part of the vector W that's sort of going down the hill. And of course, to keep this car from rolling down the hill, you would have to overcome whatever this vector is, right? This is what you'd have to overcome to keep the car from just rolling down the hill. So what we're going to talk about is essentially the relationship between the vector that I drew at first, which is W, and the red vector here, the new vector that's pointing down the hill from W, okay? And here, maybe I'll just put a right angle here is what I'm trying to depict, okay? So how do we do this? So I'm going to take two vectors, V and W, and of course, given any two vectors, you can always position them so that they have the same initial point. And furthermore, I can sort of turn it so that one of the vectors is just conveniently pointing horizontally, okay? So I'm going to choose to do this, okay? And maybe I'll make this a little longer. And here, okay? This vector at the bottom I'm going to call V, and this one will be U. Okay. Now what I'm going to do is take a perpendicular, I'm going to drop it down from the tip of U down to V. So I'm making a right angle right there, okay? And what I'm going to be interested in is the vector that goes from the common initial point here, sorry, technical difficulties. Whoops. Okay. The common initial point here out to where I dropped that perpendicular there, okay? So I'm just going to highlight this in maybe green. Okay, so first I'm going to calculate the length there of that green bit, okay? I just want length. I'm not thinking about the vector. I'm just thinking about how long is that green bit, okay? So I'll call that X. Now we all know trig. There's an angle here, which I'll call theta. This is a right triangle that we're looking at. So from our trig, we know that the cosine of that angle is adjacent over hypotenuse. Well, the hypotenuse is a vector, so I want the length of the hypotenuse, which is just the norm of that vector. u. Okay? So x equals norm u cosine theta. Okay? So I'm actually going to just erase x now and put that. The length here is the length of u cosine theta. And I don't think your book says this, but this length is called the scalar component of u along v. Scalar because, of course, this is not a vector. This is just a number. This is just a distance here. It's just the scalar component of u along v. So in the direction of v here. Okay? So that's what we use here. And by the way, this all would work just as well if that angle were obtuse. I'll draw that type of a setup. It's the same idea. Now theta is obtuse, so down here is my v, up here is my u. If I did the same deal, oops, let's just make that there. This time the green part is here. So I'll highlight it. It's here. It's this. But this is still norm u cosine theta. Cosine theta is negative in this case, but that's just fine. So this is a negative number now. So it's right. So I'm just going to redraw this picture really quickly on the new page. V and U. All right, so what we're after is this vector here. I'm going to draw it in green again. We just calculated the length. The length of this vector, I'm going to call this vector W1. The length of W1 we just calculated to be the norm of u times cosine theta. Okay, that's the length. So, if you notice, this expression is also sort of baked into the dot product. So let's just recall the dot product of u and v is, of course, norm u, norm v, cosine theta. Okay, so norm u cosine theta, just dividing by norm v, norm u cosine theta is just u dot v over norm v. Okay, so that will be useful in a second. Now, this vector w, w1, it's pointing in the same direction as v, and it has this as its length. Okay, so that's the length. So how do we cook up this vector? Well, it's pointing in the same direction as v, and this is its length. So if we just took the unit vector that's in the same direction as v, that has length 1, right? We talked about that last time, that unit vectors have length 1. If we took the unit vector in the direction of v and multiplied it by this scalar, then that will be exactly this vector w1. Again, I'll just say it one more time. We take the unit vector in the direction of v, and then we scale it by this scalar Now, instead of having length 1, which is what a unit vector has, it has this length, and it's going in the same direction as v. So that is exactly the vector W1. Okay, so that's what I'm about to do. All right, so next page. So if you remember the unit vector in the direction of v, well, how do we get a unit vector? From last time, we just scale by the norm of v. So 1 over norm v times v is the unit vector in the direction of v. Okay, and so here we are. W1 is u dot v over, whoops, what was it? Norm v times 1 over, oh shoot. Which this is, well, I've got 2 norm v's on the bottom and I've got a dot product on the top. So I'm just going to gather all scalars and put them out front. Of course, the dot product is a scalar. This denominator, norm v squared, is a scalar, squared, because I've got one here and one here. And I'm going to multiply that. This is actual multiplication times v. So this vector is called the vector projection of u along v. Okay, so this is also known as, so I'll put AKA, the orthogonal projection of u onto v. Okay, so 2 mouthful, but I'm just going to draw the picture one more time here. Here's v. It's as if we just sort of took a light up here, this is u, and we shined it down on this vector u, and it just casts like a shadow onto v. And so when it does that, you get this vector w. So it's just, you can think about this, or w1. You can think about this as the part of u that's running in the direction of v. Okay, so this can happen for any 2 vectors. So just your working definition is you can think of this, so you're thinking of this is u, and you're thinking, this is, I'm going to erase some of this now because this is your thinking box. This is the part of u, okay, I don't have enough space. Part of u that is in the direction of v. Maybe instead of saying in the direction, I'll say parallel, because that's a little bit more accurate. Okay. That is parallel to v. Okay, so that also works if the angle is obtuse. Okay, so if the angle is obtuse, here's our picture. Here's v. Here's u. Here's the angle theta. Well, then w1 is over here. It's going in the opposite direction. This is w1. Okay, so I changed my wording because clearly w1 is not in the same direction as v. It's in the opposite direction, but it is parallel. Okay, so W1 is parallel to V. So this is the part of U that's parallel to V. The notation for W1 is proj. So P-R-O-J, the projection of U onto V. So I would write the projection, and this is just what I was calling W1 a second ago. I would write the projection of U onto V is, again, I'm just writing again, U dot V over the norm of V squared, all of this, times the vector V. Okay? So great. So now we've got one part of U that's running parallel to V. Well, there's another part of U that's running perpendicular or orthogonal to V. So in my picture that I've got already sitting here, that would be this vector right here. And that's what we're going to call W2. Notice W2 is also sort of a portion of U, but now W2 is perpendicular to V. W2 is perpendicular or orthogonal to V, and W1 is parallel to V, okay? So what you see me here doing is decomposing. I'm decomposing U into two parts. One part is parallel to V. That's my W1. And the other part is perpendicular to V. Perpendicular to V. And I forgot my hat up here. And that's W2 in the picture. So we spent all this time coming up with a formula for W1. W2 is a little easier because if you just look at this picture, what do you know about vectors? Well, it looks like U in this picture is just W1 plus W2, right? So just notice that U, oh no, okay, here we go. U is W1 plus W2, okay? So you can solve for W2 just by subtracting, okay? W2 is just U minus W1. And that's the last thing we'll say. I'm going to change colors back to black. W2 is just U minus W1, which is just U minus, U dot V norm V squared times V. Okay, this is W1. So what we just did was prove the following theorem. Here's the theorem. 3.3.2, the projection theorem. And it says if U and V are vectors in Rn, and V is not zero, the zero vector, then U can be expressed in exactly one way, in the form U equals W1 plus W2, where W1 is a scalar multiple of V, Sometimes this thing doesn't like to write. Okay. Okay, so W1 is a scalar multiple of V. That's exactly the parallel part, right? We know that vectors are parallel if one is a scalar multiple of the other. So this is the parallel part. And W2 is orthogonal to V. Okay, so a parallel part and a perpendicular part. Okay, and this is how you find each. So we've got time to do just one example. So here are two vectors. They're going to be in R3. 2, -1, 3, and 4, -1, 2. Okay, so I'm going to find the vector component or vector projection. Sometimes you'll see this written as projection of U along V. And then we'll find the orthogonal component of U maybe I should say the component of U orthogonal to V. Okay. Okay. So two things. So the vector component of U along V, we're going to just need the dot product of U and V, and we're also going to need the norm of V squared. Okay, so the first thing is I'll just remind you of the formula. The vector component of the vector projection of U along V is U dot V norm V squared, and I multiply that by V. Okay, so first I'm just going to get the dot product. So this is number 1, number 2. Okay, so the dot product U dot V is, I'm just going to do this quickly. I'm doing 2 times 4, which is 8, plus 1 times -1 times -1 is 1, and then plus 6, so I get 15. And I also need the norm of V squared. Well, the norm of V squared is, I know, another way of saying that is just V dot V, right? That's the norm of V squared, which is 4 squared, which is 16, plus 1 squared, or -1 squared, plus 2 squared, which is 4. Okay, so that's 21. All right, so looks like I have everything I need. So this fraction here is just 15 over 21. And I guess that reduces to 5/7. Okay, so U dot V over norm V squared is 15 over 21, which is 5/7. And I just take this and I multiply that by V. I just scale V by 5/7. So the vector projection of U along V is just 5/7 times V. V is 4, -1, 2. So it's this guy, 27, -5/7, and 10/7. So this is the part of U that's running parallel to V. Okay, that's what this is. So now for the part of U that's running perpendicular or orthogonal to V. So we just need to do U minus the vector projection running along V. Okay. So basically, it's just 2, -1, 3, minus the vector we just found. Okay, let's see, get that straight mark. Okay, and I've done this ahead of time, and if I didn't make any calculation error, this should just be -6/7, -12/7, 11/7. Okay. This is the vector, the part of U that's running orthogonal to the vector V. Okay? That's enough for now.